Hello and welcome to Principles of Mathematics lesson number 13. In this lesson, we're going to learn about the greatest common divisor and the least common multiple of two or more whole numbers. The greatest common divisor and least common multiple of two or more whole numbers can be found using a variety of methods, and we'll look at some of the more efficient methods in this lesson. We're also going to look at application of the GCD and LCM to word problems and their solutions. GCD, of course, being an acronym for greatest common divisor, and LCM an acronym for least common multiple. We'll also look at the Euclidean algorithm in relation to the greatest common divisor. Here's a nice problem to kind of get us motivated to learn about the greatest common divisor. We have two bands that are to be combined to march in a parade. A 24-member band that's going to march behind the 30-member band. The combined bands must have the same number of columns. Each column must be the same size. So these are the two requirements, right? They have to have the same number of columns, and they have to, each column must be the same size. We want to know what is the greatest number of columns in which they can march. Now, obviously, since both of these numbers are even, we could simply break them up each into two columns, right? And that would work, but that wouldn't satisfy the requirement that it would have to be the greatest number of columns in which they can march. So if you think about it, that is going to require us to break both 24 and 30 up in such a way that the same kind of breakup occurs, meaning of the same size, right? So in other words, we're looking for the greatest common divisor of 24 and 30. So that means the largest number that goes into both of them perfectly. And if you think about it, that number is, I'm going to let you think about it, 6, right? So we can break up both 24 and 30 into groups of 6. So that means the 24-member band is going to break up into 6 columns, and each one of those will have 4 members in them. The 30-member band can also be broken up into 6 columns, but notice that each of those columns will have 5 members in them. So the situation will look somewhat like this. So we're going to have the 24-member band in the back and then the 30-member band in the front of them. So we'll have 1, 2, 3, 4, 5, 6 columns. This is the 24-member band, each having 4 members, right? And let's say 2, 4, 6, right? And the 30-member band is also going to be broken up into 6 columns, but there are more people there, so each of those columns is going to have 5 members in it. Like so. All right, so now you can see that the combined bands will, of course, form columns of length 9, right, with 9 people in each of them. And of course, 9 times 6 is 54, which is the same as the original number that we started with. So that's how you would break it up. So there's a really quick, nice application of what the notion of the greatest common divisor can do for us. So to formally define it, the greatest common divisor, or the GCD of, it's also called the greatest common factor of two whole numbers a and b, in which case not both of them are 0, is just going to be the greatest whole number that divides both a and b. The reason, of course, we don't want them both to be 0, because then we would be forced to pick 0 itself as the GCD, and as we know, we cannot divide by 0. 0 cannot divide other numbers. That's an undefined operation. So therefore, we have that stipulation to take care of that possibility. So as a real simple example where we just saw, for example, that the GCD of 24 and 30 is 6, right? Now, we also know, for example, the GCD of, say, 15 and 25, for instance, would be 5. Now, as long as one of the numbers is not 0, we're okay. For example, the GCD of 0 and 6, right? And this may be confusing at first, but if you think about it, makes sense. It would be 6. Why? Because 0 is divisible by 6. How many times? 0 times. And so is 6 is divisible by 6, which is 1 time. So the greatest common divisor of 0 and any non-zero number would be that non-zero number. How about the GCD of, say, 12 and 17? Now we know that 17 is a prime number, right? So the only factors that are going to go into it are 1 and itself. So the only common factor these two have is in fact 1, because you remember, the worst case scenario for GCD is 1. You can't do worse than 1, right? So because 1 goes into every whole number, right? So here, when we have two numbers like this, we know that the GCD is going to be 1. In this case, where the GCD of two numbers is 1, we say that these two numbers are relatively prime. So we can say 12 and 17 are relatively prime. That's the word that we use. So to generalize, we say if the GCD of two numbers A and B, two whole numbers A and B is 1, then A and B are relatively prime, which just means they don't have any common factors other than 1. Now, be very careful not to fall in the error that one of them has to be prime. No, for example, consider the GCD of 25 and 36. Notice neither 25 nor 36 are prime numbers. Why? Because we know 5 goes into 25, for example, which is a number other than 1 and itself. Or for 36, we know 6 goes into it, which is a number other than 1 and itself. So both of these are composite numbers. However, they have no common factors other than 1. So here we have two numbers, neither of which is prime, but they are relatively prime. Why? Because the greatest common divisor between them is 1. So therefore, remember the triangular dot formation in mathematics means therefore. Therefore, 25 and 36 are relatively prime. All right. Make sure you understand these simple facts before we proceed. For teaching this to younger students, here's a nice method. It's the colored rods method. We want to find the longest rod such that we can use multiples of that rod to build both the 6th rod and the 8th rod, right? So here you can see the longest such rod would be a 2 rod, because these 3 of those 2 rods and 4 of those 2 rods here can do the trick. So there's a nice visual way of understanding the greatest common divisor. Another method for finding the greatest common divisor of two numbers is the intersection of sets method. We list all members of the set of whole number divisors of the two numbers, then find the set of all common divisors, and finally pick the greatest element in that set. Let's take a look at an example. Suppose here we want to find the GCD of 20 and 32, right? We denote the sets of divisors of 20 and 32 by D20 and D32 respectively, right? So notice we have for divisors of 20, we have 1, 2, 4, 5, 10, and 20. These are all the unique numbers that go into 20 perfectly, right? For 32, we have 1, 2, 4, 8, 16, and 32. So the intersection of these two sets, the set of common divisors, is basically the set containing the elements 1, 2, and 4, right? So here are basically here we have the set of the common divisors of these two numbers. So since we want the greatest common divisor, we're just going to pick the largest of those numbers, and that will be our GCD. So this is the intersections of sets method for finding the greatest common divisor. Certainly works, but not the most efficient method. We'll find better ways as we proceed. All right, in most situations, the method of choice for finding the prime factorization of, for finding the, greatest common divisor of two or more numbers is the prime factorization method. To find the greatest common divisor of two or more non-zero whole numbers, basically what we do is we find the prime factorization of each of them, and once we have the prime factorization of both, we identify which factors are in common, and then the GCD is just going to be the product of the common factors, each of them raised to the lowest power of that prime that occurs in any of the prime factorizations. And we've already talked about what relatively prime means. Numbers such as 4 and 9, whose GCD is 1, are relatively prime. Now, this is one of those scenarios where words don't do us a whole lot of good, do they? So now watch it in action and you'll see how much that makes sense. Okay, let's go ahead and find the greatest common divisor of, say, 108 and 72. So we already learned how to a nice way of finding the prime factorization of a whole number in a previous lesson. The method I'm referring to was the one, if you recall, where we write each number and then put a line next to it, and now we're just going to start looking for the smallest prime number that goes into that number, right? So obviously it's an even number, so it's a no-brainer. The smallest prime number that goes into an even number is always 2. We go ahead and divide 108 by 2, we get 54, and remember we write the result on the right below the 108. Now we repeat this process and keep going until we get a 1 on the right side, okay? And then we're done, we have the prime factorization. So at each step, ask the same question. What's the smallest prime number that goes into this number? Again, if you notice, it's even, so it's going to be 2. We write it down, we divide, and 54 divided by 2, that's 27. We write it below the 54. We keep going. What's the smallest prime now that goes into 27? It's no longer 2 because this is an odd number. So we try 3. 2 plus 7 is 9. Remember, if the sum of the digits is divisible by 3, the number is divisible by 3. And of course, we know that 3 goes into 27 9 times. So we write the 9 below the 27. Repeat the process. So 9, we know again, is divisible by 3. When we divide, we get 3. We put it under the 9 here. Now we have a prime number, and we know that the only prime number that goes into a prime number is itself. So we write 3, and then when we divide, we get 1. Remember, once we get to 1, the process is finished. Now we have the prime factorization beautifully laid out for us on the left side. So notice that we can write 108 as 2 squared times 3 cubed. All right, we will now go through and work the same method for 72 to find the prime factorization of 72. You should definitely pause the video, do this on your own, and then come back to the video. All right, 72. Now, we start with 2 again because it's even. 72 divided by 2, that's 36. We write the 36 here below the 72. Once again, that's even, so we know the smallest prime that goes into that is 2. We go ahead and write it, and we divide. 36 divided by 2 is 18. We put that below the 36. Now 18 is even, so again we can go with 2. 18 divided by 2 is 9. Now we have to move on to 3 because we know 3 goes into 9. So 9 divided by 3 is 3. We write it on the right side. And finally, we know that 3 goes into itself. So we get a 1 on the right side, and we know we're done. So notice that 72 is 2 cubed times 3 squared. Okay, now for this first example, I do want to actually write that out because then you can see why the procedure that is described on the previous page and I'm about to reiterate will make sense. So that's 2 times 2 times 3 times 3 times 3, right? Remember, normally we won't do this, but just for an explanation, this first time that we're doing this process, this will be very helpful. Times 3 times 3. So notice that they have, let's just circle all the common ones, right? They have one factor of 2 in common. They have another factor of 2 in common. They have one factor of 3 in common, and then one more factor of 3 in common, right? Notice that that is all they have in common, right? So just take one of those factorizations and multiply that out, and you will get your GCD. So the GCD of 108 and 72 is basically 2 times 2 times 3 times 3, which is 4 times 9 or 36. All right. Now, normally the way we're going to approach it is this, and now this will make sense to you. So once you have that 108 equals 2 squared times 3 cubed, and that 72 is equal to 2 cubed times 3 squared, you're going to find the common factor. So you're going to write your GCD in the following way. Without having to do all this, you're going to look at these and say, what are my common factors? We notice both 2 and 3 are common factors. So for each common factor, write the base and then the lowest exponent that you see. Why? Because remember, that's just going to catch the ones that are in common. If you use 2 cubed, that's too many. Then you've caught one that is not actually in common. So we go 2 squared times, and we do the same thing with 3. So between 3 cubed and 3 squared, we're going to pick 3 squared because, again, remember, we only want the ones in common. If we picked the 3 cubed, we would have picked this one, which is not in common. So we have 2 squared times 3 squared, and of course, again, we get 36. So generally, this is what we're going to do. For this example, I laid it out so that you can understand. Now, the second part we've already seen, right? The greatest common divisor of 0 and any non-zero number is just going to be that non-zero number, because it's simple. Because notice, 13 divides 0 and 13 divides 13. How many times does 13 divide 0? In other words, what's 0 divided by 13? That's just 0. So 0 times. And what is 13 divided by 13? 1 time. Okay? So remember, the GCD of 0 and any non-zero whole number is just going to be that non-zero whole number. All right, so make sure that you have this process down before you proceed. All right, let's go ahead and find a few more GCDs. In this case, we want to find the GCD of two numbers x and y, where x is given by 2 cubed times 7 squared times 11 times 13, and y is given by 2 times 7 cubed times 13 times 17. So in this case, the hard work of prime factorization is taken care of. You just need to really understand what the GCD is based on the procedure we just spoke about and apply it. So again, for all of these, make sure that you pause before you proceed to watch me do it. And that's how you really learn math, by being involved in the process. All right, so notice that the GCD of x and y is going to be, now let's look at the numbers that they have in common, the prime numbers that they have as common factors. They have 2 in common, 7 in common, and 13 in common. So what you could do is put a marker for yourself so that you don't forget. So notice they have the factor 2 in common, the factor 7 in common, and the factor 13 in common. And there's no other common factor. So what we're going to do to find the GCD, remember, we scan these, and for every common factor, we take the lowest power. Remember, that's because we want it to be common to both. So between 2 cubed and 2, we're going to select 2, because that's 2 to the 1, right? We don't write the 1, but it's there. So between 1 and 3, 1 is less, of course, so we take that one. Between 7 squared and 7 cubed, we take the 7 squared, and remember, we're going to multiply all these, right? So times 7 squared, and then for 13, they're both of the same power, 1, so we just pick one of them. It makes no difference. Just make sure that you don't take both, you just need it once. All right, and that's it. So we're just going to multiply that out to see what the GCD is. Now, when you're doing homework, make sure you pay attention to the format that they request. Sometimes they might just say leave your answer as a product of powers, or they may say simplify it and write it as one whole number. So assuming they want the whole number, we'll just go ahead and get it. So 2 times 7 squared times 13. All right, in case you're wondering if I got a new calculator, no, this is the same calculator. Under the skin, I chose the compact mode today. Previously, I was on the horizontal mode. So it's the same calculator. You just have options for the skin, okay? So 1274 is our GCD. And that should not be surprising, because once you multiply each of these, those are very large numbers. So it's not surprising that the GCD is this large. Okay, how about this part? Again, pause, then come back. All right, so we have 3 numbers here we're trying to find the GCD of. So be very careful. We're going to scan and look for common factors to all 3 numbers, right? So we do notice they all have 2 in common. We'll put a marker. We also notice that they have 7 in common. I mean, if you want to be even more descriptive, you can use different colors if you like. But I mean, as long as you're careful, you can get away even with one color. So, or you could do, for example, if you don't want to use different colors, you could use double bars, you know, like let's say, up here, I could have double barred the 7s and say bar and circle the 13s, if you want to have different symbols. Now, we do notice they have 2 in common, and if you notice, they also have 7 in common as a factor, right? So we go ahead and mark those as well in all of them. And that's it. They do not have 11 in common because 11 is in this one but not in the other ones. 13 is in 2 of them but not in the third one, etc. So remember, 2 and 7 are the only common factors. So now we're going to do our procedure, right? Which is to go through, pick the lowest of each common factor's power, and then multiply. So for 2 cubed and 2, we're going to pick 2, which is 2 to the 1, right? And for 7 and 7 cubed and 7 squared, actually, let's go back to 2. There's 3 of them. 2 cubed, 2, and 2 squared, right? We're still okay, but I just want to make sure that you're looking at all 3 of them, okay? So between 2 cubed, 2, and 2 squared, we pick 2. For 7, between 7 squared, 7 cubed, and 7, we pick what? We pick 7. Because that's just 7 to the 1, which is of course less than 2 and 3. And we multiply it out. So this time our greatest common divisor or greatest common factor is 14. All right, did you do this one yet? If not, go think about it for a minute and come back. All right, so if you take a look, what factors do they have in common? Well, none of these that we see, right? But remember, there's always that hidden common factor, isn't there? That one that you can think of as being multiplied by each one, right? So remember, the worst case scenario, the smallest greatest common divisor possible is 1. So the greatest common divisor of these two numbers is 1. So what can we say about x and y in this particular example? X and y are, finish my sentence. Yes, I heard you, you're right. They're relatively prime. All right, good for you. Remember, anytime the greatest common factor between two numbers is 1, then they're relatively prime. Be very, very careful before you make this determination that these are all prime factors, okay? Be very careful because, for example, if somebody gives you x equals 5 to the 4 times 13 to the 10 and another number 3 to the 10 times 25 to the 5, for instance, be very careful. Even though these look different, these two are actually related, aren't they? So you can't make this determination if all the factors are not prime. Here, this factor is not prime. But remember, when we do this procedure, this whole procedure depends on what? On prime factorization. So this should not have been there to begin with, right? So the correct way for that to have been written would be to think of 5 squared, 425, and then raised to the power of 5. So this should have been written as 5 to the 10, in which case you can see there is a common factor. So these two numbers would not have been relatively prime. So be very careful with that. All right, let's go ahead and move forward. All right, so there is a way to use modern calculators to find the GCD of two numbers. Now, keep in mind, you do need to know the methods, so please don't abuse this. I am going to share it with you because it is the era of technology. You should be familiar. However, the way that many of the problems, and for example, on the homework or the test are going to be stated, it's going to force you to know the actual methods that we learn to do this by hand. But think of this as a way to check your answers to make sure you've done it correctly, not as a way to do the problems. Unless, of course, the instructions say use a calculator to find the GCD. So the way you would do that on, say, HP prime is quite nice. We're going to use the prime factorization method, but we're going to get some help from HP prime. So the command you would use here would be I factor Make sure you type it correctly, because otherwise it'll give you an error. And then we're going to write the number we want to factor. So I'm going to find the prime factorization of 120, and there's the prime factorization of 120. And now we'll do the same command for 180. And there it is. So now we can easily write the GCF, right? So notice they have a common factor of 2, 3, and 5. For 2, we're going to use 2 squared. For 3, we're going to use the lowest power, 3. And for 5, they're both the same power, so we'll just use 5. So 2 squared times 3 times 5. Okay, so 2 squared times 3 times 5. And of course that's 4 times 5, which is 20 times 3. Notice how I used compatible number method to do that quickly in my head. 4 times 5 is 20 times 3 is 60. So there we did that using a little bit of technology. All right, so let's move on. All right, another method for finding the GCD is called the Euclidean Algorithm method. And we're going to state it and use it, but not prove it. The proof is not actually beyond you, and it's readily available if you do a quick search on Google, etc. However, it's not the purpose of this class, but we do want to learn it and use it. So it's quite clever. What it states is that as long as you have 2 whole numbers and A and B, and A is greater than B, then the GCD of A and B is going to be the same as the GCD of R and B. Now, what is R? R is the remainder when you divide A by B. So to bring this to life and make it not seem so abstract, let's look at an example. Let's say you want to find the GCD of, we'll do a simple example just to demonstrate at first. Let's say you want to find the GCD of 40 and 60. Well, let's put it in the same format to be consistent. We'll put the number A, which is larger, first, and then the smaller number second. Okay, just to be consistent with that statement of the theorem, okay? So what we're going to do is we're going to divide the larger number, 60, by 40. So we know we get 1, 40, and a remainder of 20. So this is the R that is being discussed here. All right, and notice that it's going to be the same as the GCD of R, which is this number, with the smaller of these two numbers, so B, so 40 and 20. So just think like this, okay? Now, of course, instead of writing GCD of R comma B, which is 20 comma 40, I can of course write the bigger number first and then the smaller number, the remainder. Why am I doing that? Because I want to use the theorem again. Remember, it doesn't mean that I can only use it once. So now I can apply it again. So I know that the GCD of 40 and 20, because 40 is larger than 20, is going to be the GCD of the remainder when I divide the larger 40 by the smaller 20. So if I do that, I get 2 this time, 40, and notice 0 remainder. Now, in fact, this procedure ends once you hit that 0, because now you're going to say this is equal to the GCD of 20 and 0, right? Well, it would be 0, 20, but of course we know that the GCD of 0, 20 is the same as the GCD of 20, 0. And now notice we're done, because we know that the GCD of 0 and any non-zero whole number is going to be just that non-zero whole number. So here we get 20. So a really neat, handy way to sometimes really quickly find the GCD of two numbers without having to go through prime factorization and all that. All right, so make sure that you understand this, repeat it a couple of times if you need to, and then we'll move on. All right, we're on the same slide. I want to tell you a little bit about theorems. Now, since this is a provable fact, in fact, it has been proven, we call it a theorem in mathematics. In mathematics, a theorem is basically a statement that can be proven. It's different from a theory in science, because a theory in science can only be demonstrated. Mathematics is the only field within which we have a theorem, which notice it ends with an EM, and theorems can be proven. Now, sometimes once we prove a theorem, we can use it to prove like a lesser fact, but which relies on that theorem. Then we call it a corollary. Now, I want to show you a really neat and quickly obtainable corollary of this theorem. And that is the fact that the GCD of two similar numbers, a and b, where a is greater than b, is going to be simply the GCD of a minus b and b. Let's see why that's true. Well, think about it. I'm dividing the larger number a by the smaller number b. I don't need to know what they are. I know that since a is larger than b, it's going to, b is going to go into a at least once, right? So if I multiply 1 by b, what do I get? B. So the remainder will be what? A minus b. So all I'm doing is I'm taking r and replacing it by what? By this remainder. And we just get the GCD of a minus b and b. And let's see how that can actually work out very quickly for us. All right, let's say we want to find the GCD of the year we're currently in, 2023, and say 2021. All right. Now, of course, we could sit there and try to go through the prime factorization method and all that, but watch how cleverly we can do this almost instantly using the Euclidean algorithm in this format. So using the corollary of the Euclidean algorithm. Notice that this is going to be, according to this corollary which we just came up with. Try to say that 3 times quickly. All right. So it's going to be the same as the GCD of the difference between the two numbers. Of course, the larger number minus the smaller number. And the smaller number. Now, that means it's going to be the GCD of, remember, 2023 minus 2021, that's just 2. And 2021. Now, that's a prime even number, and that's a much larger odd number, right? So there's no way 2 is going to go into that number because it's odd. And what is the GCD of these two numbers going to be? 1. So a very nice, quick application of this corollary. All right, let's move on. Okay, let's go ahead and do a problem where we use the Euclidean algorithm a little bit more extensively. Let's say we want to find the GCD of these two numbers. All right, so of course we know that this is the larger number and this is the smaller number. So we're going to do this with some help from technology. We're going to go ahead and divide the larger number 10,764 by the smaller number 2,300. So we end up with 4 and some change, right? We're really interested in the 4 because once I write it up as a long division, I get let me do it on this side so I can bring my calculator. So now I'm going to multiply 2,300 by 4. So we get 9,200. And now we go ahead and subtract. So 10,764 minus 9,200. We get 1,564. So now we know that the GCD of the two numbers 10,764 and 2,300 is going to be the same as the GCD of the remainder and the smaller of those two numbers. And I will go ahead and write the remainder, which is the divisor, which is larger now, and then I'll write the 1,564. All right, so now we need to repeat the procedure, right, with these two numbers now. So now we're going to apply the algorithm to these two numbers. So again, we're going to do what? We're going to divide 2,300 by 1,564. So we get 1 and some change. So when we write it as a long division, notice we have this time 2,300 divided by 1,564. We get 1, so that's going to give me 1,564. And I'm going to go ahead and subtract. So 2,300 minus 1,564 is going to give me 736. So I know that this is going to equal to the GCD of the remainder and the smaller of the two numbers. So, and I will write the 1,564 first, just so that I have it as the large number coming first. And 736. All right, so we repeat the process. We're going to divide 1,564 by 736. So we get 2 and some change, so we put the 2 here, and we go ahead and multiply 2 by 736. That gives us 1,472. We'll subtract. So we end up with 92. So we know that this is going to be the same as the GCD of the remainder and that number, which was the smaller of the two. So I'll write the 736 first, and then I put the 92. All right, again we repeat the process, so we divide the larger number 736 by 92. I mean, if you had to do all this by hand, this division, this would have been a rather nasty process, but since technology is here to help us, so we get 8 perfectly, right? So that means, of course, that 8 times 92 is 736. But just to convince you, okay? So we get the remainder of 0. And of course, you know, this process ends once you hit 0, because now I can say this is equal to the GCD of the remainder and the smaller of the two numbers, so 92 and 0. And remember, the GCD of 0 and any non-zero whole number is just that non-zero whole number. So we just found that the GCD of 10,764 and 2,300 is 92. All right, a really, really nice algorithm. Okay, so make sure you master that before we proceed. All right, so here's another problem that I would like you to do, either using the Euclidean algorithm or the corollary that I showed you. Think about this for a minute. You should be able to figure this out. It's very clever. If you remember the trick I showed you with the corollary, you should be able to zap this very quickly and then come back to the video. All right, so to answer this quickly is going to require for you to understand that the GCD of 3 numbers can't be any larger than the GCD of any 2 of them, right? Think about that for a minute, that statement, and see if that makes sense to you. All right, consider this. Let's say we just want the GCD of 12, 18, and 30, right? Now, we know the GCD of 12 and 18 is 6, right? Well, can the GCD of the 3 of them be any larger than 6? That would be impossible, right? So, in fact, we know the GCD of 6 and 30 is also 6, so this would be the GCD for all of them. But the point is, the GCD of all 3 cannot possibly be larger than the GCD of any 2 of these numbers, right? So that's the fact that we're going to use here. So let me go ahead and erase that now. So we're going to focus on the GCD of 2 of these numbers that are given right here. Now, if you remember from the corollary, we decided that the GCD of 2 numbers like, well, let's give you the general form. The GCD of A and B is the same as the GCD of A minus B and B. Remember? If not, back up the video and you can watch it again. So that indicates the GCD of 6341 and 6339 is going to be the same as the GCD of their difference, and 6339. Now, that's just 2, right? 6341 minus 6339, 2. So this trick should look familiar to you, right? Now, this is the smallest prime number, and that's an odd number, so they obviously aren't going to have any common factors other than 1. So that's 1. So what does that tell you? Therefore, and we remember that the GCD of all 3 can't be larger than that because that's the GCD of 2 of the numbers. So therefore, the GCD of 134,791, 6,341, and 6,339 is going to be 1. All right, a nice application of the corollary that we discussed. Here's one more nice application of that corollary. Let's say you want to prove that the GCD of any two consecutive whole numbers is 1. Here it's given to you in the form of find, but you could have easily turned this into a theorem and proven it. So prove that the GCD of any two consecutive whole numbers is 1. So any two consecutive whole numbers can be written in this form, right? If the first one is n, the next one will be what? 1 more, right? So n plus 1. Now we know that this is going to be the same as the GCD of their difference and the second number, right? The smaller number. Because between n and n plus 1, which one is the larger number? Obviously n plus 1. So according to the corollary, the GCD of A and B, as long as A is greater than B, is going to be the GCD of A minus B and B, right? So in this case, this right here plays the role of A minus B, and N plays the role of B. And of course, what is N plus 1 minus N? That's just 1, right? So it's going to be the GCD of 1 and N, and regardless of what that whole number is, the GCD of 1 and any whole number is just going to be 1, right? So this is a nice proof that the GCD of any two consecutive whole numbers is 1. All right, here's another real nice application, a little bit more real life oriented than some of our more mathematical examples and applications. So hot dogs are usually sold in packages of basically 10, and hot dog buns are usually sold in packages of 8, and which I think is actually true. What is the least number of packages of each you must buy so that there is an equal number of hot dogs and buns? All right, so I think by this point you realize this is nothing but an LCM problem, right? What we need to do here is we need to find the LCM of 10 and 8. The least common multiple of these two numbers. So what is the smallest number that they both go into? Now, there's a really interesting relationship between two numbers, say A and B. The GCD, the greatest common divisor, is the smallest number that goes into both of them. The least common multiple is the other extreme. It's the smallest number that they both go into, right? So let's take a real simple example of, say, 6 and 9, right? So what is the largest number that goes into both of them, right? If you think about it, it's 3, right? That's what we say is the GCD. Now, on the other hand, there's another number of interest to us, which is the smallest number that they both go into, right? Think about that, what that would be, and I think you will realize that would be 18. So this interesting relationship exists between these two numbers. There's another interesting relationship between GCD and LCM, which we will learn soon. But for the time being, since we haven't learned any algorithms for finding the LCM, it's very easy. Just start writing some multiples of 10 and some multiples of 8 and see what is the smallest one where they come together. So what are some multiples of 10? Well, we have 10 itself, 20, 30, 40, 50, 60, etc., right? Now list some multiples of 8. So this is a very crude way of finding the least common multiple, but it works. So we have 8 16, right? I'm just multiplying by 2, by 1, by 2, by 3, by 4, so 32, by 5, so 40, by 6, so 48. Notice I can already stop because I have found the smallest number, which is a multiple of both 10 and 8, right? So basically, we would have to go with 40 as the least common multiple of 10 and 8. So what does that mean? Does that mean I have to buy, 40 of them? No. Remember, hot dogs are usually sold in packages of 10, right? So in order to get 40 hot dogs, I would have to buy 40 over 10, so that means 4 packages of hot dogs. And since the buns are sold in packages of 8, I would have to buy 40 over 8, which is 5 packages of buns. So if I buy 4 packages of hot dogs and 5 packages of buns, I'll have the exact same number of hot dogs and buns. And that's how you would approach a problem like this. And this is a perfect example of where the least common multiple comes into play in mathematics. So notice 4 packages of 10 hot dogs will give me 40 hot dogs, and 5 packages of 8 buns will give me 40 buns, so that then I'll have what? The exact same number of hot dogs and buns. And that's the least number of packages where this will happen. Of course, remember, any multiple of that will do too. So if you have more guests, just double that. Go for 80, right? Which means you would buy what? 80 divided by 10, which is 8 packages of hot dogs, and 80 divided by 8, which is 10 packages of buns, etc. So just any multiple of that will do, okay? Make sure that makes sense to you before we proceed. All right, so formally speaking, the least common multiple LCM of 2 non-zero whole numbers A and B is the least non-zero whole number that is simultaneously a multiple of A and a multiple of B. All right, so in other words, as we said, here you have A and B. Find the smallest number that they both go into, and that will be the LCM of A and B, as opposed to the GCD, which is the smallest number that goes into both of them. Okay? There we go. All right, so here's a very visual way of finding the LCD. It's very powerful, and it helps younger students understand it. Let's say we want to know the least common multiple of 3 and 4. So we start putting arrows, right, of size 3, and we just keep going for a while, right? And then we start doing that with arrows of length 4, right? And then just do that for some time. And then see where the 2 arrows are going to end, the arrow tips are going to end at the same place. And if you notice, it's right here. That's how you know 12 would be the least common multiple of 3 and 4. So a very visual, very, very crude and very inefficient method, but very powerful in really driving the concept home, right? So one should never be obsessed with efficiency, because sometimes the most efficient methods are the worst methods when it comes to actually understanding concepts. Efficient methods should only be introduced after the conceptual methods have been mastered. In that case, you don't get in any trouble. There is both understanding and efficiency. But when you only teach quick, fast methods and you don't teach the foundation, then there's no depth and there's no understanding. There's just robotic going through motions, and you don't want that with yourself or your students. Okay, the colored rods method is another really nice visual way for younger students to understand the concept of LCM. We basically start placing some 4 rods and then some 4 rods up here, sorry, and some 3 rods, and see how many we need till they match up perfectly. So another really powerful visual method for students to understand the concept of the least common multiple of 2 numbers. The intersection of sets method is very similar to the approach we had for finding the greatest common divisor using intersection of sets, but in this case we'll list all the set of positive multiples rather than factors of the 2 integers, and then find the set of all the common multiples, and finally pick the list element in that set. Let's see how that works. Now, we should make a little bit of a correction when we say find all the multiples, because remember, whereas the factors are a finite number, the multiples of any number are not finite. There are infinitely many multiples of any number, right? So for any whole number, we have a finite number of factors, but an infinite number of multiples. So we only need to list some in order to get a grasp of what needs to happen. So here we have 8 and 12. We're going to list some multiples of 8. We've already done this. We do the same with 12, and we can see some common multiples along the way, right? And the set that's in the intersection of those 2 sets looks to be in this manner, right? Multiples of 24. So the smallest of these numbers is of course 24, which will be our least common multiple. Again, a very crude method that actually works, but we will again find a more efficient method like we did with the case of a GCD. Okay, let's go ahead and find the LCM of these 2 numbers, and we're going to use a much more refined method called the prime factorization method. It's going to be a similar beginning to the way we found the GCD. And once you find the prime factorization, the beauty of it is you can quickly find both the GCD and the LCM of 2 numbers. And I will show you that in a minute for both. At first it looks like the task of finding the prime factorization of these huge numbers is very daunting, but if you just start doing it, you'll see it actually, the process terminates rather quickly for most scenarios. So let's go ahead and start with 2520. All right, so we know that it's an even number, so we can start with dividing by 2. So that gives us 1260. It's even again, we can divide by 2 again, so just have your calculator handy. This should be an easy task. We see that it's even again, so we can still stay with 2. So 2 again will give us 315. Now, remember, when the number ends in 5, always try divisibility by 3 before you jump to 5, because then your numbers will be nicely ordered, okay? Your prime factorization. 3 and 1 is 4, and 5 is 9. 9 is divisible by 3, so I know my number is going to be divisible by 3. Now, 1 plus 0 plus 5, that's 6, so we're still divisible by 3. So we divide by 3, we get 35. Now 3 and 5 is 8. This number is not divisible by 3, but I know it's divisible by 5. So I divide, I get 7. And of course, the only number, prime number that goes into the prime number 7 is itself. And I end up with 1 on the right side. I know I'm finished, okay? So let's go ahead and do this for 10,530. If you haven't done so already, please pause the video and do that on your own and then come back. All right, welcome back. Let's see if you got this. All right, so notice it's an even number. That means we can start with dividing by 2. So 10,530 divided by 2. So I write the 2 on the left side. Remember, nothing but primes on the left side here. So 2 is the smallest prime number, so that gives me 5,265. I write that on the right side. Now, this is no longer even, but let's see if it's divisible by 3. 5 and 2 is 7, 7 and 6 is 13, and 5 is 18. 18 is divisible by 3, so I know my number is going to be divisible by 3. I divide it, and I get 1,755. Now 1 and 7 is 8, and 10 gives me 18, so this is still divisible by 3, so I go with 3 again, and I divide it. And we get 585, and 585, that's 10 and 8 is 18. Again, we can divide by 3. So one more 3 gives me 195. Now 1 plus 9 is 10 plus 5 is 15, which is divisible by 3. So 195 is going to be divisible by 3. So I divide by 3 again, I get 65. And now I know that's 11, so that's not going to be divisible by 3 since the sum of the digits is 11, but I know it's divisible by 5 because it ends in a 5. So we divide by 5, we get 13. And 13 is a prime number, so the only prime number that will go into it is itself, and we end up with 1 on the right. Notice how relatively quickly that was done, even for these really large numbers. So keep that in mind when you want to panic about this the next time. Okay, there is nothing to panic about. So we just discovered that 2,520 equals 2 to the power of 3 times 3 squared. Let me get rid of this now. So 2 cubed times 3 squared times 5 times 7. Now, 10,530 we have discovered is 2 times 3 to the power of 1, 2, 3, 4. So 2 times 3 to the 4 times 5 times 13. All right, so when we were looking for the GCF or the GCD, we only looked for the common factors and we took the lowest power, right? But remember, this time we're looking for a number that's large enough so that both of these numbers go into it. That means it's got to be big enough to cover all these powers, right? So that means you do the opposite. You look for not just common factors, but all factors, and you multiply not the smallest power, but the highest power of all factors to get your LCM. So that's the procedure. Find your prime factorization and then go through, and this time take the highest power of any factor that you see. Okay, so for 2 we pick 2 cubed. For 3 we pick 3 to the 4. We need a 5 because it's there. We need a 7 because it's there. And we need a 13. Now this is large enough for both of those to go into. In fact, I can demonstrate for you quickly. Like, let's look at the LCM and divide it by the first number. And I'll do it in factored form. So I'm going to divide it by 2,520 in its factored form. See? Now notice we can cancel, the 2 cubes cancel. 3 squared goes into 3 to the 4, 3 squared times. 5s cancel, 7s cancel, and you get what? You get 9 times 13, which is 90 and 27, right? So 117. See, we just showed that 2520 goes into the LCM perfectly. How many times? 117 times. You can do the same thing with 10,530, and you'll see that it will also go into the LCM perfectly, because look, we designed it that way, right? All the highest powers are accounted for and every factor is accounted for, so it is going to go into it perfectly. All right, so that is how you take care of the LCM. Now, should you want to know what the actual number is, of course, you just multiply it out. So you just do 2 to the power of 3. Oh, not the answer, be careful. 2 to the power of 3. Now notice the cursor, it's at the exponent level. I need to hit the right arrow to get it out of there. So times 3 to the power of 4, again hit the right arrow, times 5 times 7 times 13. And that gives me 294,840. So that is the LCM of these two numbers. All right, let me erase this down here real quickly because I want to show you something else. And that is this fact. I told you, once you have the prime factorization, you can find both the GCF and the LCD very quickly. Notice that for the GCF, or the GCD, we usually call it, right? Doesn't make any difference, same thing. It's going to be now, for this, you only pick the common factors and the lowest power of each common factor and multiply. So for 2 and 2 cubed, we pick 2. For 3 squared and 3 to the 4, we pick 3 squared. For the 5s, which is the last common factor, we pick just 5 itself, right? That's the lowest power. All right, then we multiply it out. So that's actually quite small. That's 90, right? Remember, we used compatible numbers. We did 2 times 5 first, which is 10 times 9 gives us 90. All right, so that's the nice thing about this procedure. All right, so let's see if we can kind of summarize what we do to find the GCD and what we do to find the LCM. And remember, both of the procedures that I'm going to mention here are after we have found the prime factorizations, right? So once you have found the prime factorizations, you're going to multiply the lowest powers of only the common factors. All right, so that's like a really long acronym, right? But you know what that stands for? Multiply the lowest powers of common factors. For the LCM, you multiply the highest powers of all factors, not just the common ones, but all. So notice that a little bit of what appears to be a counterintuitive thing. For the greatest common divisor, you multiply the lowest powers of the common factors. For the least common multiple, you multiply the highest powers of all the factors. This one, only common factors. For this one, all factors. All right, so make sure that you have that completely down. Maybe do a couple of other examples for yourself to make sure you have this down, and then we'll proceed. All right, so we've already learned about a nice connection between GCD and LCM of two numbers A and B. Remember, you have A and B. GCD is actually the largest number that goes into both of them. And the LCM is the smallest number that they both go into. So they're really two extremes, right? So again, the greatest common divisor is the largest number that goes into both of them, and the least common multiple is the smallest number that they both go into, right? Well, there is one other really nice connection between GCD and LCM, and that is the fact that if you take the GCD of two numbers and multiply it by the LCM of the same two numbers, you just get the product of the two numbers. Now, this is actually a theorem. We can prove it, and the proof of this one is really nice and very much in line with the skills of this class. So let's go ahead and do it. Do try to pause the video, see if you can come up with it yourself, and after you've tried it for a bit, come back. Remember what the maybe I'll start with a hint for you, right? Remember what the GCD of two numbers is, right? And what that implies, and that should help you proceed with the proof. All right, so let's do the following. So here's the theorem, and now we're going to prove it. So we just write proof. All right, so let's go ahead and give this guy, the GCD, a name, right? So let's let D be the GCD of A and B. All right, to bring this to life, we're going to run a sample example on the side, okay? This will really help you. So let's look at the GCD of, say, 6 and 8. Now, we know the greatest common divisor of 6 and 8 is 2. But think of what that means, right? That means there is some number that if I multiply 2 by, I get 6. And there is some number that if I multiply 2 by, I get 8. Isn't that true? Okay, so that would be 3 for the case of 6, and that would be 4 for the case of, that would be 3 for the case of 6 and 4 for the case of 8. All right, so we're going to say then, let's get a little bit mathematical here. There exists, remember a backward E means like that, capital E means there exists. Two numbers, remember here I just call them, so notice this D plays the role of 2 here. And the two numbers 3 and 4 here, we'll just call them M and N when we generalize. So there exists Mn belonging to the set of whole numbers, right? So there exist two whole numbers M and N such that, remember when you put a backward epsilon with dots around it, the way you read that is such that A, which is being played by 6 here, is equal to D times M, and B, which is being played by 8 in our example over here to the right, is going to be D times N, right? So now in this very basic format, you can see that the LCM of A and B is going to be, look, if I just multiply the 2 by the 3, I don't need to repeat the 2, so I need to multiply by 4. That will give me the LCM, won't it? So the LCM of 6 and 8 is just going to be 2 times 3. And remember, we don't need to repeat the 2 because it's already taken care of, but we will need that 4, right? So notice that works, right? That's 24. In fact, the LCM of 6 and 8 is 24, right? The least common multiple of 6 and 8. So here we'll say the LCM of A and B is going to be D times M times N, right? If you get confused, just look at our example, right? So we've established what the GCD is. It's called D, right? Right here. And now we know what the LCM is. Let's go ahead and multiply them because that's what we're trying to establish, a result about the product of the GCD and the LCM, right? So now we say, therefore, the GCD of AB times the LCM of AB is going to be, well, look, we have D here, right, times the LCM, which is DMN like that. But look, because of associativity and commutativity, I can do this product in any order that I want. So for example, I could put M first, then D, and then N, and then another D, right? Notice these two are exactly the same. But remember what MD was, or DM? Okay, let me write it like that so that it looks more consistent. So let's go DM, DN. Same thing, right? Remember what DM was? That was A. And do you remember what DN was? That was B. Hey, what did we just prove? We just proved that the GCD of AB times the LCM of AB equals AB. And that's a beautiful result. So once we're done with the proof, we usually write QED. So what does that stand for? Latin, quod erat demonstrandum. That means that which was to be shown. In other words, the proof is finished, okay? We just accomplished what we were asked to accomplish. That's what that means, QED, okay? Not to be confused with QED from physics, which stands for quantum electrodynamics. So we're not talking about that QED. We're talking about the Latin version, which has to do with mathematics. All right, make sure you can run something like that. It will do wonders for your mathematical comprehension. All right, let's go ahead and move on. Okay, so this is going to be our last example of the lesson before we look at some homework problems. But here we want to find the LCM of 731 and 952, but we want to use the fact we just learned, okay? So that means you don't have to find the LCM directly. You should be able to do it by first finding the GCD. So we can use either the Euclidean algorithm or the prime factorization method. So in order to keep this video to a reasonable length, I'm going to use the prime factorization method, but we're going to go ahead and get some help from our calculator, okay, to do this a little bit more quickly. So let's go ahead and see if we can find the GCD of 731 and 952 using technology. All right, so remember the command I factor of, you need parentheses, so we're just going to put 731, right? 17 times 43 for that, and now we'll do the same command and 952. All right, so here are the two factorizations, correct? So the only factor they have in common is 17, and they're both the first power, so we can see that the GCD of those two numbers is going to be 17. Remember, we're looking for the greatest common divisor, so the procedure tells us once we have the prime factorization to pick to multiply the lowest power of all common factors, and there's only one, so it's just 17. So now we're going to use this fact to get the LCM. In other words, we're not going to go through and find, even though we could do it easily, we want to use this fact, right, for some practice. So since the GCD of 731 times 952 times the LCM of 731 times, and I'm sorry, comma, 952 is equal to their product, meaning 731 times 952. All we're going to do is solve this simple equation for the LCM. That means we're going to divide both sides by the GCD. All right, so notice these guys will cancel out. We just end up with the LCM of 731 and 952 being basically the product 731 times 952 divided by the GCD, which we have just found to be 17. So now we go to our calculator, we just do 731 times 952 divided by 17, and there we have our LCM. Using the nifty fact that we learned about the relationship between the GCD and LCM of two numbers. So there is the LCM of 731 and 952. All right, so that's it for our lesson. As usual, we'll go ahead and look at some homework problems now. All right, we covered many examples during the lesson proper, so we don't really need to do that many of these, but we'll look at a few nevertheless. Here is one that's going to use the fact we just learned. It gives you the product of two numbers and their GCD, and it wants their LCM. Well, remember, we can do that easily because we have that nice connection between them. Namely, the fact that the GCD of two numbers times, I'm just going to write GCD times LCM. We know we're talking about the two numbers, so it's going to be their product, right? Let's call them A and B, right? So A times B. So I'm looking for the LCM, so I need to solve this equation for LCM. So again, we're going to divide both sides by the GCD. And here again, the GCDs will cancel out. So the LCM is just going to be the product divided by the GCD. So the LCM we're looking for is going to be AB over the GCD. Now we know the product. It's given. It's 1587. Divided by, we know the GCD as well, so it's 23. So now we're just going to do that division, and we'll get our answer. So we do 1587 divided by 23, and we get 69. There it is. So a real nice quick application of what we just learned. All right, so here we have 14 boys and 7 girls at a party, and the host wanted each to be given exactly the same number of candies that could be bought in packages containing 15 candies. what's the fewest number of packages that could be bought? So obviously, the first thing we need to figure out is the total number of people at the party, right? Total number of individuals. And that would be 14 plus 7, which is 21. It goes without saying that you should always try these before you watch me do it, right? That's the most effective way of learning. So now, notice that we're going to, because there are 15 candies per package, that means we're going to want to know what's the least common multiple of the total number of people and 15, right? So we're going to find the LCM of 21 and 15. So we get, that's going to give us the number of candies, right? So that could be shared equally among them. So 21, we find the prime factorization. 3 gives us 7, 7 gives us 1. So there it is, very quick. 15, 3 gives us 5, 5 gives us 1. So 21 equals 3 times 7, and 15 equals 3 times 5. So the LCM is just going to be, remember, take the highest power of each factor, or all factors, not just the common ones. We're finding the LCM. So 3 times 5 times 7. Now, that's 15 times 7, which is 10 times 7, which is 70, and 5 times 7, which is 35, so 105. See, as you get better at these, you can do this in your head. So basically, we need 105 candies if they're going to be shared among them. So now you have to figure out the number of packages, right? So we take the total of 105 candies and divide it by 15. Now, here's a clever thing to do, so you don't have to use a calculator even. We know what 105 is in factored form. It's 3 times 5 times 7, right? So you can divide it by 15. Of course, 3 times 5 is 15, so these two cancel the 15, and we end up with 7 packages. All right, nice quick application. Okay, here we have an example that really helps us make sure we understand the relationship between LCM and GCD. So we have two distinct natural numbers, A and B. It's extremely important, that fact, because otherwise some of our answers would not work. So distinct means different, right? So they're not the same. So for example, here in part A, we're asked if it's true or false that the LCM of two numbers divides the GCD of those two numbers, the same numbers. Now, if you remember, we have two numbers A and B, and the GCD is the smallest number that goes, here we go again. The GCD greatest, the greatest number that goes into both of them, and the LCM is the smallest number that they both go into, right? So as we've seen, for example, with 6 and 8, as a simple example, the GCD is 2, whereas the LCM, if you recall, is 24, for instance, right? So generally speaking, the LCM is going to be a larger number than the GCD. So is it true that the LCM divides the GCD? Is the GCD divisible by LCM? No, generally not, right? If the numbers are different, it's always the other way around. If this said the GCD divides the LCM, yes, that would always be true. Now, I want to make sure you understand that there is one very special case in which this could become true, but remember, when we say something like this, we mean generally. The only time when the GCD and LCM of two numbers actually are equal would be when? Think about that for a minute and then come back. Pause, think about that and come back. Okay, I think I heard you say if the numbers are equal, and you would be exactly right, okay? That's the only time, like 2 and 2, 6 and 6, right? In that case, the GCD and LCM would be the same, this would work, etc. But here we're saying different numbers, distinct numbers. So that can never happen for distinct numbers. So this first one would be false. The LCM, the least common multiple of two numbers, divides the product. Of course, look, the product here would be what? Would be 48, for instance, right? Yeah, of course, the LCM is the least common multiple of two numbers. So the product is always going to be a multiple of both numbers, and it's oftentimes larger than the LCM. So yeah, the LCM does divide the product. That's true. The GCD of two numbers is less than or equal to the first number, for example. Of course, the GCD is the greatest common divisor, so it's going to be less than or equal to both of those numbers, right? 2 is less than or equal to 6, and 2 is less than or equal to 8, for example, and yes, that is generally true. And LCM, is that generally greater than or equal to both numbers, either number? Yes, that's also true. So again, you just have to reason these out very carefully and you'll be fine. All right, so here's the last problem we want to look at, and it's an interesting question. Is it true that every common divisor of two non-zero whole numbers a and b is a divisor of the GCD of a and b? If you think about it for a minute, it's in the very name, right? The GCD is the greatest common divisor of two numbers. So clearly, every other divisor is going to be a divisor of the GCD. All right, that should wrap it for this lesson. Go ahead and take care of yourself, and we'll see you for the next lecture.